In this video, I'd like to delve a little bit deeper into the notion of having a complex derivative. It's not enough to have a slope going in horizontal and vertical direction. They somehow have to work together for the complex derivative to exist. Somehow, this restriction is nicely summarized in what's called Cauchy-Riemann equation. It's the secret sauce that somehow describes this. Let's jump right to it. Okay, so Cauchy-Riemann equation. So let's start with a simpler function and then build up to deriving this equation. Okay, we're gonna switch back to our point of view into multivariable real functions. So suppose we have a function f of z, break that up into the real part, which is a function of the real and imaginary part of the input z, and the imaginary part of the function we're going to call v. Okay. Example. So we've actually already done this computation with z squared, but let's try it again. So we could rewrite z as x plus iy. And if we square this by foiling it, that's the real part of the function z squared. And this is the imaginary part of the function z squared. Okay, so you can break up the functions u and v in this way. We already know that the function z squared is an entire function, so it's complex analytic. So the derivative in a complex way exists. And we know the derivative to be equal to 2z. Okay. So let's look at what the function u and v are doing as we take derivative in the direction x and y. Okay, so imagine we fix y as a constant and take derivative with respect to x of this function u. Okay, so I'm treating x as a variable and y as a constant. Then the derivative is equal to 2x. Again, similarly, let's take the y and fix it in the function v and take the derivative with respect to x. So we're treating both 2 and y as constants and x as the variable. Derivative is going to be 2y. Okay. Now let's see what the derivative would be if we instead fix x and take the derivative with respect to y. So derivative of u with respect to y is going to be negative 2y, because that's the only part that's variable. And derivative of this guy, thinking y as the variable, we'll just have 2x. And you might, when you see this, you might realize that there's some similarities, right? Like 2x is similar, and 2y, well, that's not the same as negative 2y, but it's also similar. Is this a coincidence? And the answer is no, not really. Well, we know the derivative is 2z. So 2z is the same thing as 2x plus I 2y if you break it up into the real and imaginary parts. And notice 2x appeared as the derivative here, and 2y appeared as the derivative here. So, I mean, really the derivative is going to be derivative of u with respect to x plus I times derivative of v with respect to x. But then again, we could also rewrite this. It could also be written as the derivative of u with respect to y plus I derivative of v with respect to y, but then with negative I in front. I'll explain how I got this in a minute. Okay. Let's make sure, so z squared is a very simple function. Let's just pick a random polynomial equation that I pull out of nowhere. and then see if we get something like this again, right? Let's do it. So if I have a polynomial in Z, I could replace Z with x plus iy and multiply it all out, collect real and imaginary terms, and this is what I get for and the real and imaginary part of this polynomial 2z cubed minus 4z plus 1. I know that polynomial is an entire function. So this guy is complex analytic. Let's see if we get something similar when we take the derivative with respect to x and y and so on. Okay, so let's look at u. If we think of x as the derivative, this is what we get as the derivative, 6x squared minus 6y squared minus 4. Okay. If we take derivative with respect to y, there's only y in one term right here, so negative 12xy. If we look at v and take the derivative with respect to x, we get 12xy, which is very similar, but with a negative sign. And if we take derivative with respect to y, we get this, which is exactly the same as before. So it looks like the pattern is holding up in this random polynomial that I chose. The pattern being derivative of u with respect to x is the same as the derivative of v with respect to y. And if you do the other variable, again, you'll get something similar, but with a negative sign. Okay, let's see where this equation has to come from. Okay, so here's what we're doing. We're taking the derivative of the function along the real axis. So let's think of this h as a real number only, and let h goes to 0, right? So first, I'm going to add h to the x side, and then take the limit as h goes to 0. Well, if you group the u's together, we're going to get the derivative of u with respect to x. And if you group the iv parts together, the derivative is going to be derivative of v with respect to x. Okay, this is supposed to match the derivative along imaginary axis as well. So again, let's take the derivative as h goes to 0. I'm thinking of h as the real number here, but approach from the imaginary axis. So I'm adding h to the y part of the variable, but I'm dividing by ih because remember I'm supposed to divide by the change h when it's imaginary, but I'm making it imaginary by multiplying by I, but still thinking about h as a real number. I hope that makes sense. And again, we're gonna get this partial derivatives with respect to y, but this time I'm dividing by constant I. So dividing by constant I is actually the same as multiplying by negative I. You could get that by, you could get the equivalence by multiplying above and below by I. So I squared on the bottom will becomes -1, and we'll have I on the top. Okay, so that's where negative I came from. And after doing both of these, so remember the derivative from both directions has to be equal to each other, right? So the real parts of this has to agree. And the real part of it is going to be this guy has to agree with this guy. It becomes real because negative I times I is going to be +1. And then again, the imaginary part has to also agree when you take the derivative. And then just summing it up, this is the relation that we get. Okay. This is the same relation we had before. We're going to call this Cauchy-Riemann equations. Okay. All right. So we have a nice little equation. So does Cauchy-Riemann equation guarantee that f is a complex differentiable function? The answer is almost. It's not quite enough. You could, yes, as long as you allow a little bit nicer function. So here's a theorem, which I will not prove. Okay. F of z is analytic, and when I write analytic, think complex analytic. If and only if u and v have continuous partial derivatives and satisfy Cauchy-Riemann equations. So Cauchy-Riemann equation is doing the heavy lifting here, and having this partial derivatives be continuous is to get rid of really weird cases. So I don't want to get too much into the weird cases because it'll take time away from the class. But if you're curious, you can imagine here, this is a counterexample, something that's not complex analytic at 0. It is the partial derivatives at 0 exist, but it's not, the partial derivatives goes crazy near 0, even though it exists. Here's an example. So function e to the -1 over z to the 4th, where it's away from 0, and define the function to be 0 there. Okay. All right. So let's do an example, or actually, I want you to try an example. I want you to try checking this function f. Okay, e to the x cosine y plus I e to the x sine y. Try taking this derivative of each of these real parts and imaginary parts with respect to x and y, and see if you can plug it into the Cauchy-Riemann equations to check if this is a complex analytic function. Try it out, and I'll see you in the next video.